Good afternoon, everyone. Welcome back to class. I hope you guys had a good rest. Well, not really a rest, more like a catch up time. I hope all of you guys got caught up with all the work that you might have been behind with. So, before I start the class, are there any questions so far? I'm glad you can hear. Okay, cool. So, let us then start. We are continuing with the standard components lecture that we did last time before the holiday. Semester test 2. And then I'll show it to you. I think it's the first week in June. Test week 2, we're probably going to be doing MGC on the 7th of June. When are you going to use CAD? Well, that depends. In MGC, you'll get an assignment soon, which is due on the 14th of June. After MGC, depends what you're studying and what your interests are and where you go and work. So the question regarding whether the exams are online or not, so far everything is still online. Even as far as I know, the second semester will most likely also be online, which sucks, I know. I really do prefer doing these classes in person. Although the online stuff does kind of work in the meantime, the in-person stuff is a lot better. So for this semester, you can almost be guaranteed that the exam will be online. Yes, your next CAD lecture is lecture 19, which is the one that this group has on Wednesday. As well. I can't guarantee it. Obviously, they don't ask me for my opinion on all of this, but my guess, looking at how things are going now, that the whole semester is online and the second semester probably as well. Remember, there are many students who stay quite far away and some even in neighboring countries. So to just quickly get them on campus isn't something that can be arranged overnight. Thanks, Ms. Lewis. Yeah, I always answer the questions because I don't know which group asked what, but if this was asked here before, then I suppose there's not really a point in asking it again. Okay, cool. Let us start with the class for today then. We are continuing with the work that we did just before the holiday. I'm just quickly sharing my screen. It should come through any moment. There we go. Okay, so before the holiday, we looked at keys. Remember, a key was used to prevent relative rotation between two components. And after that, we looked at something called a circlip. So a circlip is a small spring steel component, like that green one on the slide. It's used to stretch open, move over the shaft, and relax it to click into the groove. And that is used to prevent relative axial motion between components. And if you use a key and a circlip, then you basically lock the two components together. So prac assignment 4 marks should probably be out, I don't know, probably this week sometime still. So those were circlips and keys. Let's quickly discuss repetitive features. So here I have a metal gear. This is just an example. Now you can notice this metal gear has many teeth around the circumference, and they're all exactly the same. It's just a pattern of the same one all the way around. So if you draw this thing, it would be kind of pointless to make a detailed drawing where each of these teeth are actually shown. So a shorter way to do this is to draw one of them and then just show a center line to show it is patterned all the way around. Another application could be bolts that are assembled on the same pattern. Then this could be like the bolts that hold a truck's wheel in place. So instead of drawing all of them all over the whole time, you can draw one of them and show the center lines for the rest of them. Cool, thanks for answering the question for me. Okay, next we've got a chain drive. That would be something like your bicycle. They use chain drives. So instead of drawing each link of the chain, you can now see here that a chain is a rather complex thing. It's got your pin link plate, your bushing, something that was cut off when I pasted it. There's the sprocket. There's the roller link plate. So it's actually a fairly complicated thing, although it is a standard component. So drawing a chain in detail is kind of pointless because it's a standard component. So what you could rather do is just make use of a center line to show where the teeth lie and where the chain would go. And then just draw a couple of the teeth to show the size of them. Let's quickly have a look at a chain drive mechanism. Okay, sorry for the people who get seasick very easily. Ta-da. Okay, so there we have a cut open motorbike engine on the floor in my office. So at the front here we have the front sprocket, there's the back sprocket, and basically as you rotate the one, the teeth will pull on the chain. So it pulls on the top of the chain, which causes the back sprocket to also rotate. Oh snap, sorry, I floated there. Front sprocket, back sprocket, chain. And then you can drive the back one by turning the front one. The same principle applies with the gears as well. A gear is used to link two shafts in a rotating manner. So you would have the two gears made into each other, and as the one gear turns, it causes the other shaft to turn as well. So that's a means of power transmission. So with a chain drive, you actually don't even need to show the chain link because the chain is linked to the sprocket design. So if you specify the kind of sprocket, then you automatically specify the chain size as well. So this red line over here is used to show the pitch circle for the sprocket teeth, and that red line there is the pitch circle for the sprocket on the back. And that red line and the one at the bottom is the chain path, and the outside there, and that side is also the chain path. If you're talking about that circle and that circle, then yes, you draw both of them. Now you'll notice I've got these little open blocks over there and over there. What are these? You'll remember from 3 slides ago, that is a key in the keyway. So it is used to prevent relative rotation between the sprocket and the shaft. Yes, they are keys. Thanks. Yes, for this one you would typically specify the pitch circle diameter, or what you can do is you can specify the size of the teeth, so that distance there, and the number of teeth around the circumference. So remember, a chain drive mechanism will have a sprocket on the driver's side, a sprocket on the driven side, and the chain in between. So when you draw it, you can just draw a part of the one sprocket and show the chain line to actually show the chain. I think in this case you would still, if you do a top view, you would just see the width of the sprocket and the chain will still be indicated just with a center line. Okay. Any more questions? No, you don't need to specifically know the exact names of all these things. It will get a little bit technical if we do all of that. So you'll notice in this one's case, all of the little spikes didn't have a center line. So no, you don't have to match it like that. You can literally just draw a couple of teeth and then center line to show that the pattern goes on. Typically, you would indicate the number of spikes just by means of a note. The diameter of the pitch circle will be given in a catalog of the chain drives. So these are standard components. You can literally go to a company that sells this stuff and buy a chain with a certain length from them. So then the diameters of all of these things will be nicely written up in a catalog. And it's amazing to find that there are no cats in catalog. Okay. Yes, depending on exactly what dimension you want to show, you can dimension it like that. Okay. So that was a chain drive. Next topic of discussion is something called a bearing. So a bearing is used to ease the relative movement of different components with respect to each other. We get different bearing types. First one is called a bushing, and it's also known as a journal bearing. So this is basically just a soft, smooth material that you put between two components so that the one can slide over the other one. That's like putting a blanket between your desk and the floor when you want to move the desk over the floor. Okay, the second type that we're going to look at is called roller bearings, which have rolling elements, quite self-explanatory. Then there exist many other kinds of bearings, magnetic bearings, fluid bearings, and whatever. We're not going to really focus on those. We'll just look at the roller bearings and journal bearings in MGC. Just as an example, the wheel bearing on a car is a normal roller bearing. Usually they use taper roller bearings, but also sometimes they use deep groove ball bearings. That was just for interest. You don't have to know that now. Okay, and a bushing. So just for interest, on the shaft on this side we've got this metal ring that can rotate. And you'll see on the inside it's got those little shiny balls. Those are the rolling elements. So basically this kind of bearing works on the principle of something rolling over a surface. Okay, where the other kind of bearing works on the principle of something sliding over a surface. So sliding, and that's a coin, rolling. And obviously from that already you can see, and from just a little bit of common sense, rolling bearings usually have a lot lower friction than a sliding bearing, because it doesn't have to drag one surface over the other one, it simply rolls it over. So it's like when you try to balance yourself on a soccer ball. It's a fairly tricky thing to balance yourself on a soccer ball. If you try to stand on it, you'll just roll off of it due to the very low apparent friction. Fidget spinners actually use roller bearings. They use a small kind of roller bearing. So typically, if you look at this picture, you can see it's got, this one has, it's 7 balls. 1, 2, 3, 4, 5, 6, 7. So this is a rolling element bearing, and they use that in the fidget spinner due to the low friction. So sliding is basically, as I said, like putting the carpet between your desk and the floor. Okay, so sliding typically has a slightly higher friction than the rolling ones. Yes, I'm going to do an example of a bearing in a couple of minutes. So this is an example of a bushing. So this is a metal cylinder that gets housed in some other device that clamps it down. And then you can have a big shaft that fits nicely in there, not loosely. So it mustn't like rattle around. It must fit nice and almost tight in there, but still free to rotate. Basically a clearance fit. And then this material is usually a softer material than steel. So this example is a bronze bushing. Bronze is a copper alloy. So basically what happens is the steel shaft will slide on this copper bushing. Now typically you would put some oil in between them, oil or grease, to reduce the effective friction. But I'll say more about that in a couple of minutes. Just another example of like the chain drive. This is just a little toothed belt drive. Okay, that was just a random thing. I don't even know what this was used for. So the bushing I just showed you guys, this is a sliding bearing or a journal bearing, also known as a bushing. Shaft goes inside and it slides on the surface. The rolling ones have the little rolling elements. It can be spherical, like a ball. In this case, it is spherical. Or it can even be cylindrical, like little cylinders, which will do the rolling then, depending on the type of bearing. You can even watch if I spin the shaft, it can actually spin for a couple of seconds just due to the low friction of the bearing. Yes, the sliding bearings usually have a rather higher friction, effective friction than the rolling bearings. So typically in this bushing, the outside would be held stationary in the casing, the shaft would be on the inside and it will turn. And you will use a oil or grease layer to separate the two. It's like, have you ever walked on a tile floor with flip-flops on? And the floor, if the floor is wet, then you can step as carefully as you want, your feet just slide around. So basically what happens, if this is the floor and the other hand is the flip-flop, they actually can't make physical contact with each other to transmit friction. If you have a layer of fluid on there, especially soapy fluid, then they will always be separated by a very thin layer of fluid. So basically, if you're walking on a wet floor, you're actually walking on a very thin layer of water. And that's why effectively you can just slide anywhere then. And a roller bearing like this one would typically then be like trying to walk on marbles. So each kind of bearing does it have its own advantages and disadvantages. Um, and it depends on the application as well. With this big shaft, a journal bearing can usually take, or bushing, can usually take a higher force than the roller bearings. Roller bearings can also be slightly more noisy. So what's interesting, the bearings used inside your motor car engine are actually still journal bearings. You did get some special applications many years ago where they put needle rollers on the crankshafts of Beetles, but that wasn't very successful. And what's interesting though is the friction loss inside here compared to the overall losses in your motor car engine are so small that it's not really worth trying to fix this problem. So journals are used for higher force applications. What's interesting is, just give me a second. So this shaft that I just dropped on the table here is actually a turbocharger shaft. This is the compressor wheel, that's the exhaust turbine. And these are two little journal bearings. So that little cylinder is a copper alloy and the shaft runs inside of it. And it's full of holes because oil is actually physically pumped through there to keep it well lubricated. Now for interest, this shaft, when it was still working in the turbo, this thing would typically turn 150,000 revolutions per minute. So 120 to 200,000 RPM. Crazy, crazy speed with the journal bearing. You do get ball bearings in turbochargers as well, but that's a different application. Technically, yes, bushings are used in shock absorbers. Yes, you aren't completely wrong with the statement, but it is not quite as simple as that. So I've collected these things over many years of um, engineering, fiddling, and stuff. So the turbocharger shaft came out of my dad's one, his business is one bakkie. The turbo's exhaust housing cracked, and then I took the turbo as a display item. I have some shafts in my cabinet over here, which came from my dad's vehicles, or the one differential came from my own car, which I broke the diff. It sucks to break a diff though. So I collect it wherever I can. Yeah, it's crazy fast. Some of the smaller high-speed turbos turn faster than 200,000 RPM. I don't think there would really be an application to have a combination of both roller and bushing. Yeah, you do get turbochargers with ball bearings that can spin very fast as well. But basically, the ball bearing or journal bearing isn't the physical limitation of the turbocharger. Yeah, the turbos do make a cool sound. So sliding bearing or bushing is the same thing. Oh, yes. Now I miss my supercharger. I used to have a supercharger on my car, and the wine was pretty cool. Diff is the thing at the back of your vehicle between the wheels. It basically allows you to go around the corner without dragging a wheel. On the turbochargers, it's driven by exhaust gases, so that's why they spin so fast. Mm, I don't specifically say turbocharger is better, but that's a whole discussion on its own. Um, Funny enough, the fastest cars in the world run with superchargers. Just saying. That's funny. I don't think probably 90% of the people here won't understand that comment. It was in my old Ford that I had the supercharger on there, but I had a different engine in there at that stage as well. The exams this year for MGC, I can only answer for MGC. I can't really answer for the rest. They will be the same as the semester test. I think let's leave the supercharger and turbocharger conversion for the end of this lecture, and then we can chat as much as we want. But yeah, both of them have their own things, which are good and bad. I'm quite doubtful that you'll be able to write on campus, but that was asked at the start of the session already. So let's go back to today's lecture. Okay, bushings. Bushings are usually made of a softer material than the material that it is supporting. So basically what you want is you have to use a bushing that's not the same material as the thing it's supporting. If you rub two pieces of steel against each other and they're the same metal, the one will start to eat away at the other one, and you'll actually get stuff called cold welding where they actually chemically bond in small locations and then they'll just destroy each other. So bushings are typically made of a different material. Many times, or pretty much always, it is known as a non-ferrous metal. So you'll remember iron, Fe is the symbol for iron. So non-ferrous basically means it does not contain a big portion of iron. These bushings are typically made of a non-ferrous material. It can be a metal, like in this case it is a copper alloy, or it can even be plastic. Now, something interesting that we can do when we draw a section view of a non-ferrous material, then there's actually a very practical way to indicate in your drawing that you're working with a non-ferrous material. If it was just normal standard steel, we would hatch it like we did when we did section views. Non-ferrous materials, however, are hatched in a method called cross-hatching. So we can indicate that this thing is non-ferrous just by means of hatching it differently. So that's a very handy tip. Okay, I'm glad it's not my stuff that's cutting. So non-ferrous, spelled Ferrous, non-ferrous. This is from your periodic table. This is iron. So non-ferrous just means it has very low iron in it, or no iron in it. So it can be plastic or copper or something like that. Okay, so knurling is something different. Knurling is not hatching. This is a hatching style that we will use quite a lot in our assembly drawings. Knurling is a surface texture that you apply afterwards, which is cool, but we're not going to really touch on knurling in the whole of MGC, so don't worry about that. Okay, so you won't always be told if something is non-ferrous. If it is a bushing or a journal bearing, then it will be non-ferrous. Okay. Bushings can be used to cushion movement between two solid parts, so it can help to absorb shocks and vibration as well, depending on the material of the bushing. So on the screen here, I have two different kinds of bushings. The one is to be able to take an axial force or a thrust load, and the other one is for a radial force. You basically look at where the biggest area is. It will transmit the force through the biggest area. So in this case, top and bottom, and in that case, inside and outside. So just an example of where you would typically find these journal bearings or bushings. A typical example would be in cable trolleys. So there we have somewhere the big crane, which will have them in on the inside, smaller crane in a workshop. Some of these cable cars will have it in, and this is just a picture of one of those treetop tour foofy slide cable trolleys. In your textbook, assembly exercise 2 has two bushings, and the exact example of the assembly exercise 2 is not really important for today, but basically these bushings are used to ease the relative rotation between the wheel and the shaft. So there I put the wheels on, so the bushing is inside of the wheel. When I turn the wheel, the bushing turns with it, and it slides around the shaft. So that's a typical application for a bushing. I think it's actually pretty accurate to say that the non-ferrous materials which we use for bearings and bushings have lower friction. But you do get other materials like aluminium, which actually has a ridiculously high friction coefficient. So typically the bushing materials that we will use will have low friction, but not all non-iron containing has low friction. But yes, typically you would want the bushing, otherwise it would kind of make it very hard to turn the or move the component that you actually want to be able to move. Hmm. Okay, someone just signed on and sniffed in the microphone or something. Okay, next topic is lubrication. So you remember earlier when I mentioned about walking on a wet tile floor, the layer of water on the tile floor actually causes your shoe or flip-flop or whatever you're walking on the floor with to not contact the floor. There's a thin layer of fluid between the floor and the flip-flop, which causes it to slide over each other very easily. So then adding that layer of lubrication can actually greatly reduce the effective friction. Now, for MGC, we won't be calculating friction coefficients. Okay, it doesn't help if you put your hand up. You'll have to actually ask a question. So just quickly, I see some people are saying that the screen is off. Can you guys still see my screen? So refresh it, it works. Okay, let me just quickly try screen sharing again. Okay, the screen is supposed to be off now. Okay, I've just reshared the screen. Should be up now. Okay, cool. So it seems like it is up and running again. Okay, thank you. So just to quickly say again, if my pen is now a layer of liquid, and my left hand is the floor, and my right hand is the flip-flop, when you step on it, the liquid layer actually still separates your foot from the floor, which will cause you to slide. So that's basically the whole purpose of lubrication. So lubrication is necessary when having components moving relative to each other at regular intervals. And on my student portal, it says that the semester test is in June, and I don't think that the exam timetable has been released yet. Just give me a second. I just want to show you something. So according to the timetable that we were given, the test week runs from the 5th of June up to the 12th of June, and the exam starts on the 7th of July. Examinations of first quarter, second quarter, and first semester modules starts on the 7th of July. Okay, so typically the difference here would be governed by the type of fit. So the bushing would typically be a interference fit or a transitional fit into the wheel, whereas it would be a clearance fit around the shaft. So that's why it will spin around the shaft. Yes, I think in general this isn't an incorrect statement. So yes, I think oil has less friction than water, but it also depends on what oil. You do get some pretty thin oils. Next pack would probably be released sometime this afternoon or tomorrow morning. Okay, so that was the motivation why we need lubrication. So it is used when you have components moving relative to each other at regular intervals. The mediums include oil, grease, and grease is basically just like a very thick oil, almost like butter. Water can be used as a lubricant, and even air. The marks for Prac 4 would probably be out this week sometime, let's say Wednesday. I think the best would be to email Mr. Setsedi and asking him about making a video for SolidWorks. So the question, how does air work as a lubricant? Basically what it does is, if you can force air in between the very small gap between components, then you can actually cause the one component to float on top of the other one. There's actually a very cool application for this that they use in workshops. When you have to move a very heavy machine, they put it on a flat platform of which the whole underside is sealed. So if you put a compressor on there and apply a pressure, the whole platform will be lifted slightly off the ground. Well, yes, pneumatic is basically air, exactly like air hockey and a hovercraft, yes. But the air hockey is a good example. Okay, so now the question is, we want grease on the inside of the component. Okay, so we have our journal bearing, and we don't want to have to take this whole thing apart every time and then apply grease on the inside, put it together and assemble the whole thing. So what we want is, we want a device that will allow us to put grease on the inside without opening the device. So basically what we do is we give it a channel. You can see from here, from the top, there's a hole drilled all the way through. And on the inside here, we have a groove as well. So what we do is, we use this item called a grease nipple. And basically what it does, it allows a special hydraulic pumping tool that can pump grease to click onto the end there. And as you pump the grease, it will flow in from the hydraulic line, and then it will meet that little ball at the end there. So that ball is spring loaded. As the hydraulic pressure meets the ball, it will actually push it in a little bit. So the pressure will push the ball in, and as it pushes the ball in, the grease can flow around the ball through a little channel on the inside, through there, and out the bottom. There you'll see this one has grease in it already. So now if I design my machine such that there's a location for me to screw this device in and a little passage on the inside that goes to the bearing, then it will allow me to be able to, from the outside, pump grease all the way to the inside where it is needed. So a grease nipple is a standard component and it is used for lubrication insertion. There's just a picture of the ball and the spring that keeps the ball in place. The ball and spring are necessary to act like a one-way valve. Grease can flow in, but once it tries to flow outwards, it just pushes the ball against the opening and closes it off. Yes, that is correct. That's a very good question, actually. So, old grease can be removed in a couple of ways. The normal way, what they actually do is you just pump in enough new grease that it flows from the inside outwards, and then it will push out the old grease here up the outside, and then you can just wipe it off. So in this one's case, you'll remove the old grease by just displacing it with new grease. Otherwise, you have to disassemble, wipe down, and reassemble again. So this is just a random example of a grease nipple in application. So there we have the grease nipple. We attach a grease gun to this point and hydraulically push the grease through the center of this grease nipple into the cavity on the inside. The grease will then fill up that cavity, and once it is full, it will squirt out the hole that's drilled on the side. And when it squirts out that hole, it will go into the inside of the bearing or bushing where you actually need it. So this is a very nice way to be able to, from the outside, put grease all the way on the inside of a component without having to disassemble anything. It's actually very interesting to see how they grease the shafts on locomotives. Okay, so there they lubricate the wheel, but that's not really what I wanted to show. So there, this guy is using the hydraulic pump to pump grease into the location on the inside there where it is actually needed. Okay, cool. Are there any other questions on what we've said so far today? So typically, old grease doesn't really lose its ability to lubricate, but what does happen is it gets contaminated, so it gets dirty. Basically, as the shaft rotates inside here, after time it does tend to rub away some of the surface. So some of the surface particles will be caught up in the grease, and then those particles will be carried all the way around as the shaft is rotating. So old grease will be termed old when it is dirty, basically. Well, grease is basically a liquid in the very small cap, but practically speaking, it looks a lot like butter. But oil obviously is always a liquid, unless you freeze it, but in typical applications, you don't want your oils to freeze. Okay, so how do we draw these things? If I take this example, and I'm going to make a section view of it, so we have threading, and then we have the little grease nipple in position. So that would typically be a grease nipple in application. Well, the technical term is you just use a grease gun. Okay, so the view I was drawing was this view, just in full section through the middle of the grease hole. So a grease nipple is a standard component, so we will usually not cut through it. Same as a bolt and a nut. Typically, bearing seizure occurs due to lubrication failure. Lubrication failure can be due to there not physically being enough, or it could be due to excessive temperatures. If your system is overheated, then the lubrication becomes so thin that the gap becomes too small between the two parts and they start making contact and then eat each other away. So no, a grease nipple is actually not sectioned at all. I knew it was non-ferrous because it is a journal or bushing material, which means it has to be non-ferrous. It actually doesn't, it depends on the application. For certain bearing types, like this journal bearing I just showed you, grease is ideal. But if you have high-speed applications, like this turbocharger example, then grease would actually not work at all. It just turns too fast. So in this one's case, these bearings are actually lubricated by the engine's oil. Also usually why turbocharged vehicles need a better quality oil than normal non-turbo engines. Okay, any more questions on what we've said so far today? Cool, so if there aren't any more questions, then we can stop the formal lecture here and we can continue on the discussion on turbochargers and superchargers if you want. Thanks guys, and you must have a good evening as well. So technically, please try to use SolidWorks as far as possible. I will first have to set up semester test 2 before I can give you the exact mark allocation. Usually 70% assembly drawing, 30% manufacturing. Basically, the lubrication was just an addition that we added to the textbook, but that's why it is in the slides. Okay, so basically turbocharger and supercharger. Now, an internal combustion engine, like a petrol or a diesel engine, works by converting a fuel to heat energy, basically, and then we extract the heat energy and make the wheels turn. Now, if you want the engine to deliver more power, you actually need to burn more fuel. And the problem now is your fuel has to have a certain amount of air with it to be able to burn correctly. So you get to a point where your engine, you can add more fuel quite easily, but you can't add more air because it can only suck in as much air as is physically possible. Okay, so basically a turbocharger and a supercharger are devices used to pump more air into the engine so that you are capable to add more fuel and burn more fuel and make more power. Just give me a second. On the comment of the fastest car, and you say it uses a turbocharger, then you didn't find the fastest car, not even by a long shot. I'm just quickly doing a screen share. Okay. So this is actually the fastest accelerating and close to top speed cars on the planet. They do 0 to 300 kilos an hour in about 3 seconds. Yeah, the top fuel dragsters are by far the fastest cars. Well, technically, a supercharger kicks in from very low RPM compared to a turbo, so I would almost say the opposite of what you just said. they're not road legal, not at all, but they're also the fastest car. I never said the fastest road legal car. The fastest road legal cars do make use of turbochargers, yes. That would be your Chirons and Koenigseggs and those kind of things are all turbocharged. But the supercharger on one of these top fuel reactors uses the same amount of power as what a Corvette actually makes. So if you take a Chev Corvette V8 engine, that engine just has enough power to turn the supercharger on the dragster. The Chiron, I think, makes 1,500 horsepower. These things make 11,000 horsepower. So no, superchargers usually don't have a significant or really perceivable lag. I remember on my car, if you have to really kick the accelerator to the floor to actually be able to perceive a lag. Otherwise, as you push the accelerator in, the boost goes up. The Teslas are not the fastest cars in the world. And turbo lag is not so bad. A Corvette makes about 600 horsepower, that is true. A top fuel dragster supercharger takes 500 horsepower to turn. So no, carburetor is just a fuel delivery mechanism where most modern things use fuel injection. Even the top fuel dragsters use fuel injection. But they've got fuel injectors the size of hose pipes. I think it burns 100 liters in 5 seconds. Electric cars do have high torque, very impressive high torque, but it's still nothing compared to the actual top fuels. What's interesting, your question about combining supercharger and turbocharger. Volkswagen did it on their first generation Polo GTIs, which had a 1400 supercharger and turbocharger in there. What's interesting, the pressure in a top fuel engine is about 10 times as much as the pressure in your road car. Okay, but I think the session is going to automatically end in a second now, so thanks for attending, people. I hope you enjoyed the random chat afterwards.